Hi everyone! This series of videos is going to take you through pages 29 through 32, which comprise the last main idea in this packet called Riemann sums. Just a quick note before we get too far into the actual topic. This series of videos on this playlist is going to be kind of a combination of exploratory, as in I'll give you some directions and then you'll be working independently through some of the tasks, and lecture-based, where I'll actually try to go through and do examples and talk about some of the concepts as if you're kind of developing the ideas in class. So just as a heads up, some of these videos are going to be kind of short because it's more like a series of directions. There are some of these tasks that you'll kind of be on your own to do, and then other tasks that you can follow along with me and complete in the packet while you're watching the videos. So just kind of bear in mind that some of these videos are going to be shorter than others, and that's why. Is because some of them are basically just a series of directions, like me telling you which problems you can do by yourself, and then others are going to be a little bit more in depth. Now, just as a quick kind of note, this section at the top of page 29 is actually worth taking a couple of moments to read. And if you want to pause the video just so that way you have some time to read it so that you're not juggling reading and listening at the same time, this might be a good opportunity to do that, because this will give you some context on what a Riemann sum is, especially because it's such a strange name. In case you're curious, Riemann was the name of a guy. His name was Bernard Riemann, so Riemann was his last name. And he was one of the mathematicians who started really closely exploring the area versus integral connection. And his name is now associated with any attempt to try to take a geometric approximation using curvy shapes, or curvy equations with basic shapes. It inherently doesn't sound possible, and Riemann actually acknowledged that he knows that square shapes like rectangles really aren't a very good fit for geometrically curvy shapes like parabolas or something like that. But his approach was definitely one of the close enough mentality. So again, if you have a chance to try to read this first couple of paragraphs, it might give you a little bit more context about what we're actually trying to accomplish. In essence, we're basically going to approximate an area under a curve using geometric shapes, but we're going to acknowledge right off the bat that we know it's not a good approximation. Sometimes it might be an over approximation or an under approximation, and the goal is to just understand the merits of getting close enough, especially in cases where the calculus might be really complicated and all we need is a quick estimate of an area. In those situations, a quick series of geometric problems is actually pretty okay. It's not going to give us a perfect answer, but again, if close enough is all we need, it's a pretty good way of getting something. So, the official phrase, Riemann sum, refers to the sum of the areas under a curve that we can find with easy traditional geometric shapes. In the first example, you'll see that this function, x squared plus 1, has actually been graphed 3 different times. So hopefully you can see it. It's that curvy shape that you'll kind of be able to make out in each graph. Now, in each of these diagrams, the area under the curve has been subdivided into 2 rectangles for the first diagram, 4 rectangles in the middle diagram, and 8 rectangles in the last diagram. And the different subdivisions are going to be important. You can probably already kind of tell why. The first thing we're going to do, though, is just practice our basic area skills so that we can get some numbers. Once we get some numbers, we'll have a better sense of what exactly Riemann was on about and get a better sense of why we would even bother doing this in the first place. So for each of these questions, we're going to basically find the sum of the shaded regions by finding each rectangle separately and simply adding them up at the end. Now, some of them are kind of obvious and kind of easy to figure out. Some of them, like the last one, might be a little bit more challenging. So I'll do the last one as a bit of a together example, and then I'll ask you to complete some of the other parts on your own. In the last diagram, as we mentioned, there are 8 rectangles in that picture. Now, the inherently challenging part, as you can probably tell, is that the subdivision requires that we have these kind of random points in between 0 and 1, or in between 1 and 2, that also seem to kind of coincide with the edge of a rectangle. So what we probably should infer, and rightfully so, is that if I've divided this region into 8 equally spaced rectangles, that must mean that each of these rectangles has to be exactly half a unit wide. And it is fair to make that assumption, that each rectangle is exactly half a unit wide. That gives us crucial information about the base of each rectangle, but as you know, to find the area of a rectangle, we need to do base times height. So we'll definitely need to know the heights of each rectangle. A quick observation you can make is that the height of each rectangle does seem to have something to do with the curve. In fact, if we look specifically, and I'll just use this rectangle as an example, the corner of this rectangle, and I'll highlight where I'm talking about so you can see what I'm referring to when I say the word this. The height of this rectangle that I'm kind of outlining there in pink seems to correlate to that point on the curve, meaning that edge of the rectangle, which happens to dictate the height of the rectangle, seems to be a point on the actual curve with the x-coordinate 3. So if you have the equation, and it appears that we do, the equation is x squared plus 1, we can infer that we can find the y-coordinate. The y-coordinate must be 3 squared plus 1, or 10. So that must mean that this rectangle is exactly 10 units tall. Now, in some cases, if you have a ruler and some patience, you may be able to kind of quickly use some sort of straight-edged object or something and maybe try, if you can, to kind of line up the curve, the rectangle with the y-axis and maybe count from there. But a more foolproof strategy might be to use the equation. Now, of course, that's going to get a little bit cumbersome because for each rectangle, you'll have to look at it and say, okay, well, what's the x-coordinate of the height of this point? Oh, well, that's at 3.5, so I'll need to plug in 3.5. And then this rectangle is based on the height at x-coordinate 4, so I'll have to plug in 4. And you can see that that would get kind of tedious to do for 8 different rectangles. So as a quick time-saving measure, what we may want to consider is using our graphing calculator and creating a table of values so we can quickly refer to all of the x and the y coordinates that we might need. Now, if you don't have a graphing calculator of your own, I'll take this opportunity to simply put mine on the screen, and you may want to consider pausing the video for a moment or taking a screenshot of this just so that way you have permanent access to the table, because I did try to make it count by 0.5, which is what the x-axis does seem to be counting by, and I'm going to use those coordinates to help me dictate all of the heights of each rectangle. So again, if you need to, take a quick screenshot or pause this video and copy down some of the heights onto your diagram so that way you have something you can work with. Now, I'm going to use each height to help me dictate the base times height formula for the areas that I'm going to need to find. So for example, this teeny tiny little rectangle here has a base of 0.5. Its height is based on the y-coordinate at 0.5, which is 1.25. Just going to get a little bit tight to have to try to write for each one, so I'm just going to do the best I can. The height there is 1.25. Now, that means that to do the area, I'll do 0.5 times 1.25, which, if I calculate that, 0.5 times 0.125 ends up being 0.625. So just to make sure that I'm keeping kind of a tally here, I'm going to record that number, 0.625, and I'm going to just do that same process for all of the rectangles. So for example, the next rectangle is another 0.5 units wide, so I've got that. The height of the second rectangle seems to correlate to this point on the curve, which has an x-coordinate of 1. So going back to my table of values again, at x-coordinate 1, the height was 2. And again, I'll just do my best to kind of squeeze in those heights there. So if the height is 2, then that means base times height would be 0.5 times 2, which is 1. And just because I might want to add these later, I'm going to kind of line up my decimals just to be safe. And then I'm going to repeat this process all the way through. Obviously, this is going to get kind of tedious, so I'm going to start picking up the pace to the point where I'm just going to kind of tell you some of these areas and hope that you can figure out my logic and where I got these numbers from. But just to make sure you're still with me on my logic here, I'm going to do a couple more. This third rectangle has a height dictated by the x-coordinate at 1.5. So according to my table, at 1.5, the height was 3.25. And again, doing base times height to find the area of the rectangle, 0.5 times 3.25 is 1.625. So I'll add that to my tally. The fourth rectangle, again, base is 0.5. Height of the fourth rectangle is dictated by this point on the curve with its x-coordinate 2. At the x-coordinate 2, the y-coordinate is 5. So 0.5 times 5 is 2.5. So basically, I'm just going to repeat this process all the way through, and I'm going to just keep getting area after area after area. Now, with 8 of them, which is kind of a lot, it might take a little bit of time. So as long as you can kind of follow my logic here, I'll just go ahead and give you the next few rectangles and spare you the details about how I got there. The next rectangle with the x-coordinate 2.5 had a height of 7.25 and an area of 3.625. The next rectangle after that, which now I've lost count, has an area of 5. The seventh rectangle, there I am, the seventh rectangle with its x-coordinate at 3.5 has an area of 6.625. And the eighth and final rectangle, which is the one here with the x-coordinate 4, has an area of 8.5. Now, of course, because the instruction said find the total area of the series of rectangles, series implies there's a sum involved, you'll simply add up all of your individual areas. So by doing that quickly, just to save, again, a little bit of time, we'll find that the sum of all of those values is 29.5. Which as a number is essentially meaningless right now. We don't really have much context for this, but I think you'll find that that number does get a little bit more interesting once you take a look at the other two answers that you get for the middle and the first rectangles in the diagrams. So I'm going to pause the video at this point, actually stop the video entirely, and I'm going to ask you to do letter A. Once you finish letter A, most of the questions underneath it are kind of observational. They're just going to ask you what you noticed about the answers that you got, which diagram best approximates the true area under the curve. So if you can, try to just go through those thought exercises. None of these questions are really tricky. It's just mostly asking you to kind of take into account what the difference is between those diagrams and which one gives you the truest area under the curve. The only question that you'll kind of be on the hook for doing calculus, like by yourself, is number 1, letter E, where it says find the value of the area algebraically. Algebraically implies that we're actually finding, through calculus, the integral from 0 to 4 of the curve itself, which was x squared plus 1 dx. Now that answer is going to represent the true area under the curve. So it'll be an interesting comparison once you get all 3 of these answers to the diagrams to see which one, if any, was the closest to the actual value of the algebraic area. So however long it takes you is fine. Just try, if you can, to do this series of questions and check your answers using the online answer key. Once you feel like you've actually made a couple of observations, or at the very least finished the task and felt like you understood what you were doing, then on the next video in the playlist, we'll resume on page 30 and hopefully kind of make some connections.